Let's look at complementary arithmetic for binary numbers. We will look at signed magnitude and at 2's complement. So in binary numbers, an n-bit word can represent 2 to the n non-negative digits, or integers. In order to allow positive and negative numbers, the most significant bit can be designated as the sign bit, where 1 would be used for negative numbers. The lower bits then represent the magnitude of the number in straight binary notation. So this means that if you have an 8-bit signed magnitude number, you can represent numbers between minus 127 to plus 127. So although used, this format has 2 disadvantages. One, it has 2 representations for 0. So you could have 1 and then all zeros, that would be negative 0, or 0 and then all 7 zeros, and that would be positive 0. And then secondly, it requires 2 different arithmetic circuits in order to be able to process and do arithmetic on positive versus negative numbers. And we would like to have one set of arithmetic hardware circuits that can function on both positive and negative numbers. So let's look at 2's complement notation. This is a better notation for computers, one that's easy to implement in hardware, and it's based on the fact that adding the complement of a number is equivalent to subtracting the number, and we'll demonstrate this. So a complement is that which completes. The n's complement of a number x is equal to n minus x. So for example, the 10's complement of 7 is 10 minus 7, or 3. And so when we add 7 and 3, we get 10. So 3 complements 7 by completing it. So 9 minus 7, for example, could be evaluated by adding 9 and the 10's complement of 7. So when we do that, we would get 9 plus the quantity 10 minus 7, and that would give us 12. We would then drop the final carry to arrive at 2, which is the answer. Now, it's easier to evaluate 9 minus 7 than it is to evaluate 10 minus 7. And the reason is that in 10 minus 7 you have to borrow. And this becomes particularly appropriate or applicable when you have multiple digit numbers. Taking the 9's complement of each digit can be done by inspection, followed by adding 1 to arrive at the 10's complement. So, for example, if we do a minus b, and let's assume those were 2-digit numbers like, say, 54 minus 26, then we could write a plus this would be the 10's complement, or it would be 100 minus b, and then we'd subtract the 100 off at the end. That's taken off that carry. But we could also do a plus and do the 9's complement of b by simply doing 99 minus b, then adding 1, and then we remove the carry at the end. Let me show you what this would look like for 2 examples. So in the first example, say a is 85 and b is 32. So what we could do is we could do the 10's complement. So we'd do 85 plus the quantity 100 minus 32, then remove that carry. So that would be 85 plus 68, and that's 153. We drop the final carry and we arrive at 53, which is the answer. But an easier way to do this would be to take the 9's complement right here, the 9's complement of 32, and then add 1. So when you take the 9's complement, we simply just do 9 minus 3, that's going to be 6, and 9 minus 2, that's going to be 7. So that's what we mean by saying you can do this by inspection. So then we have 85 plus 67. We add the 1 to get to the 10's complement, and then we remove the carry at the end to arrive at 53. Now, this may all seem like, what in the world are you doing? Hopefully this will make more sense in a minute when we go over to the binary side of things. One last example, let's say that we had a 3-digit number, so 234. So there we would do 234 plus the 9's complement of 32. So we're going to do 0 minus 9 is 9 right here, and then 3 minus 9, that gives us 6. And then 2 minus 9, that gives us 7. And then we'll add 1 to get the tens complement. And finally we remove the last carry. So you do all that addition and you end up with 1202. Take off the carry and you get 202, which is the answer. Now notice that what's important here is that these three numbers are all additions. When we have a subtraction at the end, this minus 1000, this does not take place by actually executing a subtraction function, because it's always just removing the final carry, so it's dropping the most significant bit. So what we've done is we're actually doing subtraction without ever having to execute a subtraction operation. Now that's predicated on the ability to be able to do a nines complement. And so now we're going to go look at what this means on the binary side, on binary numbers, and we'll see that it's even simpler for binary numbers. So in binary system, the arithmetic is simplified if negative numbers are in signed twos complement notation. In this notation, the most significant bit is the sign bit, so it's 0 for positive and 1 for negative numbers. We form the twos complement, just like we did the tens complement of any number, by first forming the ones complement and then adding 1. So we form, this is analogous to forming the nines complement when we were doing decimal subtraction and then adding 1. Here we're going to do the ones complement. And the ones complement is trivial to carry out. All we do to get the ones complement is any 1 gets changed to 0 and any 0 gets changed to 1. How easy is that? So let's see how this works. Let's form the twos complement of a number 0, 1, 0, 0, 1, 1, 0, 0. So the ones complement is you just flip all the bits. So we have the ones complement right here. You go from 0 to 1, you go from 1 to 0, 0 to 1, 0 to 1, and so forth. Then we add 1 to it. This is our twos complement. Very easy to do. Now here's another method that you can do that's even simpler if you remember the trick. So here's the number, the original number that we're going to subtract that ultimately from some other value. So we need the twos complement. So the first thing you do is you start on the right side and you copy down every digit until you arrive at the first 1. And then the remaining digits you flip. So the 1 becomes a 0, the 0 becomes a 1, and so forth. So those two, the method on the left, the method on the right, both do the same thing. The one on the right is just tricksy, and you're a really cool twos complement mathematician if you can do that. Okay, so here's an example. Let's perform the operation 29 base 10 minus 27 base 10 by using 8-bit signed twos complement arithmetic. So first we're going to convert both of the numbers to binary, which we've looked at before. So 29 base 10 is 0, 0, 0, 1, 1, 1, 0, 1. 27 base 10 is 0, 0, 0, 1, 1, 0, 1, 1. Now we need to take twos complement of the subtrahend. I don't say that right. Subtrahend. Yes, I think that's how you say it. The subtrahend, which is 27. So minus 27. Remember, all we're going to do is we're going to copy everything down until we arrive at the first 1, which happens to be the least significant bit here. And then we're going to flip all the remaining bits, and that's what we've done. Okay, and then finally we add the two numbers. We add 29 base 10 in binary and the twos complement of 27 base 10. And when we do that, we arrive at 10 base 2, which is 2 base 10, which is our answer. Now you need to watch out for a couple things. One is overflow, the other one is for underflow. So let's think about adding the following two numbers, 97 base 10 and 63 base 10. Notice that the sum of these two numbers is 160. Okay? But if you add these numbers, binary, you will end up with an 8-digit value, the most significant bit being 1. Which in twos complement representation is 96, not the correct 160. And the reason for this is that for 8-bit twos complement format, the largest positive number is 127, not 255, right? 2 to the 8 minus 1. So for an unsigned 8-bit digit binary number, remember that we have values from 0 up to 2 to the 8 minus 1. So we have 256 values starting at 0. So the maximum value is 255. Now we're sharing those 255 non-zero values with both the positive and the negative integer values. So watch out also for underflow. So similarly, will occur, let's see, there's a typo though. Similarly, underflow will occur when an arithmetic operation is less than minus 128. So the range of allowable 8-bit 2's complement format numbers is from minus 128 to plus 127. So you have minus 128, you have 128 negative numbers, 127 positive numbers, and then you have 0. And you add those together, and that arrives at 256, which is the number of unique words you have for an 8-bit binary number. Okay, and the 2's complement just works out that you get one more negative word than you get positive word. Okay, and as a clue to underflow or overflow, if two numbers that are to be added and have the same sign and the result has the opposite sign, then you know that either underflow or overflow has occurred.